Residents across a wide swath of Northern California were jolted by strong shaking on the morning of June 24, 2026, when a magnitude 5.6 earthquake struck near Redwood Valley in Mendocino County. Cell phones sounded earthquake warnings across cities hundreds of miles apart. Lights swayed in homes and offices. Merchandise fell from shelves, and thousands temporarily lost electrical service. The earthquake occurred at approximately 8:10 in the morning local time, with an epicenter located about 11 kilometers, or nearly 7 miles, north of Redwood Valley, at a depth of approximately 8.9 kilometers, or 5.5 miles. Within hours, dozens of aftershocks followed, transforming a single seismic event into an active earthquake sequence that immediately drew attention to one of Northern California's most important, but often overlooked fault systems, the Maacama Fault Zone. A powerful earthquake in California naturally raises a series of questions. Was this merely an isolated rupture on a local fault segment? Does it reveal increasing strain within the broader San Andreas fault system? Could movement on the Maacama Fault influence neighboring faults such as Rodgers Creek or even sections of the San Andreas Fault itself? And what is the largest earthquake this region is capable of producing? The answers lie within the remarkable geology of Northern California, where multiple fault systems share tectonic stresses generated by the relentless motion between the Pacific Plate and the North American Plate. The earthquake struck within the northern coast ranges, a rugged landscape shaped by millions of years of tectonic deformation. Unlike the broad valleys and relatively simple fault traces often associated with earthquakes elsewhere, Mendocino County sits within one of the most structurally complex regions in North America. Faults intersect, branch, reconnect, and sometimes disappear beneath younger sediments before reappearing farther away. The Maacama Fault Zone is a major right lateral strike, slip fault within this intricate network. In a right lateral strike slip system, the two sides of the fault slide horizontally past one another. If a person stood on one side of the fault and looked across it, the opposite side would appear to move to the right during fault motion. This style of movement is fundamentally similar to that observed along the better-known San Andreas Fault. The Maacama Fault extends through Mendocino County and Sonoma County, passing near communities such as Ukiah, Redwood Valley, Willits, and eventually connecting southward into the Rodgers Creek Fault system. Together, these structures form part of a broader transform boundary accommodating the movement between two major tectonic plates. Geological studies have long recognized the Maacama Fault as one of the primary active structures in Northern California, though public attention often focuses more heavily on the San Andreas Fault farther west. The location of the June 24th earthquake strongly suggests that rupture occurred somewhere within the Maacama Fault Zone or one of its associated fault strands. The epicenter lies directly within a region where geological mapping has identified numerous active fault traces extending through Redwood Valley. Researchers have increasingly recognized that the Maacama is not a single simple fracture, but rather a broad fault zone composed of multiple strands, splays, and interconnected fractures. Some recent studies have even identified previously unmapped fault segments in the Redwood Valley area, highlighting the structural complexity of the region. This complexity helps explain the immediate aftershock sequence. When a moderate earthquake occurs on a major fault zone, stress is redistributed into surrounding rock. Neighboring fractures may respond by producing smaller earthquakes as they adjust to the new stress conditions. By the end of the first day, more than 60 earthquakes had been recorded within the sequence, demonstrating that the crust surrounding the main rupture was actively rebalancing itself. The geology surrounding Redwood Valley reveals why this region remains highly active. Mendocino County occupies a tectonic crossroads where multiple geological processes interact. To the west lies the San Andreas Fault System. To the north sits the influence of the Mendocino Triple Junction, one of the most significant tectonic intersections on Earth. At this junction, three tectonic plates meet: the Pacific Plate, the North American Plate, and the smaller Gorda Plate. The presence of the triple junction creates an unusually dynamic environment. Crustal blocks experience compression, extension, uplift, and horizontal shearing simultaneously. Mountains rise, valleys form, and faults constantly adjust to shifting stress fields. As a result, Northern California experiences some of the highest earthquake rates anywhere in the continental United States. The Maacama Fault itself reflects these regional forces. Although primarily a strike-slip fault, sections of the fault zone also exhibit transpressional behavior. Transpression occurs when horizontal sliding is combined with compression. Instead of merely moving sideways, the crust is also squeezed together. This process creates uplifted ridges, folded terrain, and localized thrust faults. Geological mapping around Redwood Valley reveals numerous pressure ridges and uplifted landforms that testify to these ongoing tectonic forces. One particularly interesting characteristic of the Maacama Fault is fault creep. Unlike faults that remain locked for centuries before releasing accumulated stress in a major earthquake, portions of the Maacama appear to move gradually without generating significant seismic shaking. This slow motion, known as aseismic creep, allows some tectonic strain to be released continuously, rather than accumulating entirely for future earthquakes. Studies have suggested that substantial portions of the Maacama Fault exhibit measurable creep. Evidence can be observed in offset curbs, distorted pavement, and gradually displaced infrastructure. In communities such as Willits, creeping fault motion has produced visible deformation over time. This characteristic is important because creeping faults sometimes generate fewer large earthquakes than fully locked faults, although they remain capable of producing damaging events. The June 24th earthquake may therefore represent rupture along a segment where strain accumulated faster than creep could relieve it. Alternatively, rupture may have occurred on one of the many subsidiary fault strands branching away from the principal fault trace. The magnitude 5.6 event itself was significant, but not extraordinary by California standards. It generated widespread shaking, triggered the state's shake alert warning system, and was felt across much of Northern California, extending into portions of Oregon and Nevada. Millions of people experienced some degree of shaking, while the strongest effects were concentrated in Mendocino County and surrounding communities. Reports included fallen household items, cracked walls, disrupted businesses, temporary school evacuations, and localized power outages. Fortunately, no widespread catastrophic damage occurred, yet the earthquake raises an important question regarding the maximum potential of the Maacama Fault. Current geological assessments generally indicate that the Maacama Fault is capable of generating earthquakes significantly larger than magnitude 5.6. Depending on the length of fault involved in a rupture, scenarios in the upper magnitude 6 range are considered plausible. Some studies have estimated that a rupture involving a substantial section of the fault could approach magnitude 7. A magnitude 7 earthquake releases vastly more energy than a magnitude 5.6. Because earthquake magnitude scales are logarithmic, each whole number increase represents roughly 32 times more energy release. Consequently, a magnitude 7 event would release many times the energy generated by the Redwood Valley earthquake and could produce severe regional impacts across Northern California. Historical records provide only a limited perspective because instrumental monitoring covers a relatively short period compared to geological timescales. Paleoseismic investigations, which examine prehistoric earthquake evidence preserved in sediments and landforms, indicate that major earthquakes have occurred repeatedly along Northern California fault systems over thousands of years. The absence of a recent large Maacama rupture does not imply that such earthquakes are impossible. Instead, it highlights the fact that recurrence intervals can span centuries. Another question immediately emerging after the earthquake concerns stress transfer. When one fault ruptures, nearby faults can experience changes in stress. These changes are often measured in fractions of a bar, tiny compared to the total stresses within the crust, yet sometimes sufficient to influence future earthquake timing. Did the Redwood Valley earthquake affect the Rodgers Creek Fault? The answer is technically yes, but probably only slightly. The Rodgers Creek Fault forms the southern continuation of the Maacama system through Sonoma County. Geological mapping increasingly supports the view that these structures are interconnected components of a larger fault network. Because of this relationship, any significant earthquake on the Maacama alters the regional stress field affecting Rodgers Creek. However, stress transfer does not mean that a major earthquake becomes imminent. Earthquakes constantly redistribute stress throughout California. Most stress changes are too small to trigger immediate large ruptures. The effect of a magnitude 5.6 earthquake generally diminishes with distance, particularly when considering faults tens of kilometers away. Nevertheless, the event serves as a reminder that Rodgers Creek remains one of the Bay Area's most closely watched faults. Geological evidence indicates that the Rodgers Creek Fault is capable of producing earthquakes in the magnitude 7 range. Its proximity to densely populated areas elevates its significance far beyond that of many other Northern California faults. The same principle applies to the San Andreas Fault. The San Andreas is not a single continuous crack behaving as one unit. Instead, it consists of multiple segments, each possessing distinct earthquake histories and stress conditions. The Redwood Valley earthquake undoubtedly modified stress levels somewhere within the broader fault system, but the amount of transferred stress reaching major San Andreas segments was likely very small. There is no evidence that the June 24th earthquake suddenly accelerated the timetable for a major San Andreas rupture. Earthquake triggering generally becomes less likely as distance increases, and the energy released by a magnitude 5.6 event is relatively modest compared with the immense tectonic forces governing the San Andreas system. Discussion about whether faults are overdue requires additional context. The term overdue is commonly used in public discussions but can be misleading. Faults do not operate according to precise schedules. Geological recurrence intervals represent averages rather than countdown timers. A fault with an average recurrence interval of 200 years may rupture after 100 years, 200 years, or 400 years. Both Rodgers Creek and segments of the San Andreas Fault have accumulated significant strain since their most recent major earthquakes. That fact is well established through geological and geodetic measurements. However, accumulated strain alone cannot determine exactly when the next earthquake will occur. The Redwood Valley earthquake therefore should not be interpreted as evidence that larger neighboring faults are about to rupture. Instead, it demonstrates that tectonic strain continues to be actively released throughout the Northern California fault network. One of the most important lessons from this earthquake involves the interconnected nature of California's fault systems. For decades, researchers often analyzed faults as relatively isolated structures. More recent studies increasingly reveal that faults behave as components of broader networks. The Maacama Fault connects structurally with Rodgers Creek. Rodgers Creek interacts with other Bay Area faults. The San Andreas influences all of them through regional plate motion. Stress migrates through the crust continuously, sometimes producing earthquake sequences that span multiple fault segments. Historical examples elsewhere in California have shown that earthquakes can occasionally jump from one fault segment to another. Such cascading ruptures have the potential to generate larger earthquakes than would occur on a single isolated segment. This possibility explains why scientists carefully monitor fault interactions throughout Northern California. The aftershock sequence following the Redwood Valley earthquake offers a valuable opportunity to examine these interactions. Each aftershock acts as a miniature probe revealing how stress is distributed through the fault network. Patterns of aftershock migration can help identify hidden fault strands and clarify the geometry of the rupture zone. Early observations suggest that the aftershocks occupy a broad area rather than a single narrow line, reinforcing the interpretation that the Maacama Fault Zone consists of numerous interconnected fractures rather than one simple fault plane. This characteristic also influences seismic hazard. Complex fault zones can distribute deformation across multiple strands, but they can also create opportunities for ruptures to propagate in unexpected ways. Understanding these relationships remains a major focus of ongoing geological research throughout the Coast Ranges. From a regional perspective, the earthquake highlights the continuing importance of Mendocino County within California's seismic landscape. Public attention frequently centers on Los Angeles, San Francisco, and the San Andreas Fault, yet some of the state's most active tectonic regions lie farther north. The combination of the Mendocino Triple Junction, the Maacama Fault Zone, the Cascadia margin to the north, and the broader transform boundary creates an environment where earthquakes remain a persistent feature of everyday geological activity. Northern California alone contains several fault systems that are closely monitored because of their proximity to population centers and their potential to generate major earthquakes. Among them, the Rodgers Creek Fault remains one of the most significant. Extending through Sonoma County, this fault forms a structural continuation of the Maacama Fault system. Geological investigations indicate that Rodgers Creek is capable of producing earthquakes approaching magnitude 7. The fault's location near Santa Rosa and other rapidly growing communities makes it one of the most carefully studied seismic sources in the Bay Area. Farther south lies the Hayward Fault, often described as one of the most concerning urban faults in the United States. Running directly through densely populated portions of the East Bay, the Hayward Fault passes beneath or near cities including Richmond, Berkeley, Oakland, Hayward, Fremont, and San Leandro. Geological evidence suggests that major earthquakes have occurred repeatedly along this fault over the past several thousand years. The most recent large rupture occurred in the late 19th century, meaning more than a century has passed since its last major earthquake. Because millions of residents live directly atop or adjacent to the fault trace, even a moderate increase in seismic activity immediately attracts attention. The Calaveras Fault, another major Bay Area structure, accommodates a portion of the plate motion occurring across central California. Although sections of the fault exhibit creeping behavior similar to parts of the Maacama Fault, locked segments remain capable of generating damaging earthquakes. The Calaveras and Hayward faults are increasingly viewed as interconnected systems rather than isolated structures, raising the possibility that future ruptures could involve multiple fault segments. The San Andreas Fault remains the most recognized fault in California, and perhaps the most famous fault on Earth. Yet it is not a single uniform feature. Instead, it consists of numerous segments stretching approximately 800 miles or nearly 1,300 kilometers through the state. Some segments rupture relatively frequently, while others remain quiet for centuries. Particular attention focuses on the southern San Andreas Fault. This section extends through the Coachella Valley and the Mojave Desert before connecting toward the San Bernardino region. Geological studies suggest that portions of the southern segment have not experienced a major rupture since the late 17th century. As a result, this section has accumulated centuries of strain. It is widely considered capable of generating an earthquake exceeding magnitude 7.8, making it one of the most significant seismic threats in North America. Southern California contains several other major faults under constant observation. The San Jacinto Fault Zone is among the most active fault systems in the state. Running roughly parallel to portions of the San Andreas Fault, it has produced numerous damaging earthquakes throughout recorded history. Some researchers believe the San Jacinto Fault accommodates a substantial percentage of the relative motion between the Pacific and North American plates, making it one of the most dynamic structures in the region. The Elsinore Fault, extending through Riverside and San Diego counties, represents another major right lateral strike-slip system. Although generally quieter than the San Jacinto Fault, geological evidence indicates that it remains capable of generating earthquakes in the upper magnitude 6 to lower magnitude 7 range. Near Los Angeles, the Puente Hills Thrust Fault receives extraordinary attention, despite being largely hidden beneath urban development. Unlike strike-slip faults such as the San Andreas or Maacama, the Puente Hills system involves compressional faulting. Because it passes directly beneath one of the largest metropolitan areas in North America, even a single major rupture could produce severe consequences. The Newport-Inglewood Fault, associated with the 1933 Long Beach earthquake, also remains under continuous monitoring. While shorter than many of California's major strike-slip faults, its position within the Los Angeles basin places critical infrastructure and millions of residents nearby. The June 24th Redwood Valley earthquake does not indicate that any of these faults are about to rupture. However, it highlights a fundamental reality of California geology. The state's fault systems do not operate independently. The Maacama Fault, Rodgers Creek Fault, Hayward Fault, Calaveras Fault, San Jacinto Fault, and San Andreas Fault all participate in the broader tectonic process that accommodates plate motion along the western edge of North America. Every earthquake, whether magnitude 3 or magnitude 7, represents a small adjustment within that larger system. Most remain localized events. A few alter regional stress patterns. Together they reveal a landscape that continues evolving through constant tectonic motion. The Redwood Valley earthquake joins a long history of California seismic activity, reminding residents that from Mendocino County to San Diego, the forces shaping the state remain very much alive.